All right, that's 40 after, so let's go ahead and start it. Yeah, so I think most of you probably are aware. Next week is a midterm, right? Thursday night. I've already posted, just today I posted solutions to past midterms the midterms I posted way before the break. Hope you all had a nice break. I enjoyed my break. It's a long time ago. We were looking at my physics. So already we're jumping back into things quick, and the next week is the midterm. So the midterm will not have fluids on it, but the final will. So it's important to learn your fluids. We'll do fluids today, and on Thursday what I'll do is I'll give a midterm review, and I'll probably have more fluids to cover. I'll be talking about fluid dynamics a little bit. Today we're going to focus mostly on fluid, like hydrostatic equilibrium, density and pressure, buoyancy, these ideas. And then Thursday we'll get into dynamics and stuff like that. We'll get a little bit of dynamics again in class today, depending on how fast I go. And what else am I going to mention about that? Yeah, I posted the solutions now. So again, there's 4 tests on there, right? Lots of practice material. When you go to practice, take the practice exam like a real exam. Time yourself. No YouTube, no friends in the room you're talking to. Give yourself only the amount of time you have on the actual exam. And use your cheat sheet. And also, the rules for midterm 2, you're allowed to use 2 sides to write down notes. Right? So if you want, you can use the same, cheat sheet, or I shouldn't call it cheat sheet. You can use the same formula sheet used on the first midterm and just write it back. But you don't have to. I'm not going to go out and check and make sure you're using the same, sheet. You can put anything you want on your sheet. First, on midterm 1, if you felt like your sheet was inadequate in some way, had the wrong stuff on it, not enough stuff, go ahead and put different stuff down, right? So go ahead and use 2 sides of 1 sheet of paper for your formula sheet, get it all together, and then take the exams as if you're really taking a real exam. And then you'll have a more honest feeling about what it's really going to be like for the exam. All right, great. So fluids. Interesting topic for us. So first of all, I should define a couple of the most basic concepts we need to keep straight. We've already seen a notion of density so far in this class. We had mass density last week when we calculated the moment of inertia of a rod about its center of mass and about the end of the rod, and we calculated those things. But that was a linear mass density. That was a mass, kilograms, per unit length. But now we're in fluids, and we're going to be talking mostly, like if I just say density without a qualifier on it, without saying linear or volume or surface, what I usually mean is a volume density. Density, it's per unit volume, right? And it's a mass density. There's other things you can have as well, though, right? We have a number density if we want to know how many molecules of fluid there are, if we want to know something else. But in general, density, if I don't specify anything else about it, I mean mass density. So if you want to calculate the density of something, well, one way to do it is just if you know the total mass of the object, you know its volume, you say, all right, density, which I write as rho, not to be confused with P, unfortunately very similar symbols. So I try to make my rho's without, there's no little serif up here, there's no little doodad on that side of the P, indicating it's a rho. And that's just equal to the total mass of an object divided by its total volume. I'll usually write volume with serifs on it to distinguish it from my V for velocity, right, or speed. I often use V for that, but this is a lowercase v. So I tend to use an uppercase V, anyway, with serifs on it for volume. Whatever convention you want to use is fine, just make sure you can read your own notes. Or your own, when you solve a problem, make sure you find everything so you can distinguish everything. Great, so that's density. So what's more dense, oil or water? Who thinks water is denser? Who thinks oil is denser? There's a few takers on both sides. So every once in a while there's an oil spill. Where does the oil go? To the bottom of the top. Goes to the top, and some people will remember that the Exxon spill, or was it BP? Excuse me, BP spill. Anyway, if I should leave off the corporate labels here, there was a spill recently where the oil actually got deep in the water, in the ocean, right? And that was because there were other chemicals around that were acted as emulsifiers, or things that would connect water to oil, right? And you know more about that than I do applied chemistry classes. Bottom line, though, is that if you want to know what the density is, and there's nothing else in the mix, it's just oil or water. The oil and oil and water don't mix with each other. The oil floats, so oil has less density than water, right? So in the old days, when you bought milk, way before you guys were born, way before I was born, in fact, you delivered to your house, and it would separate. Did the cream go to the top or the bottom? Cream rises to the top, right? And in fact, skim milk, it'd skim the cream. So what has lower density, milk or cream? Cream has lower density. So many students will get confused by that because they confuse the notion of density with viscosity. They say, oh yeah, cream is this thicker stuff, right? It's like if you had to run through, it's sort of a strange idea, if you had to run through a room with lots of, say, molasses in it, right? In fact, there was a tragic, this is a long time ago again, 100 years ago, there was a tragic explosion at, I don't think, cookies there, some kind of factory, and there was molasses, and people were, they had to get through this molasses, and people didn't all make it. Well, it's better to have to run through water and molasses in a way because it's less viscous water is. But if we ask, I actually don't know which is denser, molasses or water. But for oil is more viscous, but it's got lower density. Same thing for cream. Cream's got lower density but greater viscosity than milk, right? So don't confuse viscosity and density. Great. So and that's how we calculate. If you know what the total mass and total volume is, that's how you calculate. There's other ways to calculate it, but that's if you know the total volume, total mass, that's an easy way to do it. Great. And what are the units of this? The units of density of this volume mass density, of course, are kilograms per meters to the 3rd power, right? Because it's volume. Very important to keep all that straight. There will be problems sometimes when you have to go between a linear mass density and a volume mass density. And the way you'll do that is by relating them with some area, some cross-sectional area perpendicular to the direction along which you'd like to know the linear mass density. For example, when we calculated the moment of inertia, right, of that pole rotating about its center of mass, say. In that case, suppose we knew the total mass and the total volume of that pole, we could calculate the linear mass density, which we call lambda, by saying, oh yeah, that's just equal to the total mass over the total length. And we can think of the total length of the pole, right? That pole like this. So it's got some length, and there's some area on the end. Well, the total volume of the pole, right, is just equal to what? Just the length times the area. So if you needed to convert to one or the other of these type of densities, you'd say, oh, well, what is L? That's V over A, so V, and you're going to A. So you could do it if you wanted to know what the linear mass density of something. Anyway, just to keep straight with these different densities mean and how to relate them, right? Okay, great. So this is important for fluids. We have to know what the density of things are. It'll turn out that there's different kinds of fluids with different densities. We'll often talk about objects submerged or floating in a fluid. I want to keep straight which density we're talking about. The density of the fluid or the density of the thing that's floating, the density of the thing that's submerged in the fluid, right? So I'll often have subscripts here shafted here to designate which of the densities I'm talking about, right? And what about pressure? So pressure I'm going to write either as an uppercase or a lowercase p. I'll try to be consistent about having that little serif, or whatever you call it, the little doodad sticking up there to distinguish it from this. So the book gives the definition, or a formula for calculating pressure, which I like, but we have to be careful about how we apply it. It says, pressure is force over area. And that's true. The pressure that something is experiencing can be expressed in terms of the force that's acting on it divided by the area over which that force acts. But it's important that this is the force that's perpendicular to the area. And what's tricky about that is sometimes you'll have, like the surface of my body, I'm not planar, right? There's a round surface here with some complicated shape. So if I want to know what the pressure is by relating the force on my body to the area of some piece of my body, I have to use a small enough patch of my body probably just to get so it's locally flat, right? and then I have to worry about only the force that's acting perpendicularly to that surface, right? So we'll use this in a minute to do an actual calculation, and we'll think about what direction the force is pointing and which way the area is pointing. And of course, pressure is a scalar, not a vector. So when I put F here, I mean this is the magnitude of the force. I don't mean it's the, I don't write a vector here. So this is, in other words, momentum. We've used P before for momentum, right? Mass times velocity. That's a vector quantity, little P like this without an arrowhead on top. Without an arrow on top, I would mean the length of the momentum vector. Don't confuse that with this. This is something else. Okay, great. So we've got our two important initial equations here. We got pressure and density. Really quick, I'll mention for pressure, there are many units for pressure. 1 atmosphere. So yeah, what is 1 atmosphere equal to in other units? So how much pressure are we under right now in this classroom? Yeah, 1 atmosphere. That's right. And in terms of how many pounds per square inch is that? You know, about 15. So let's think about what that means. We don't use pounds per square inch in this class, but there's units most of you are more familiar with just to get an idea of how big this is. So that's a lot, right? Square inch is this big, right? It's a pretty small area. You got 15 pounds right there. And it's everywhere in your entire body, right? That's a lot. If you express this in terms of newtons per square meter, it's a gigantic number because square meter is big, right? So if we say what how many newtons per square meter, it turns out to be 10 to the 5. And there's all kinds of conventions about exactly if it's exactly 10 to the 5 or if it's 1.01 10 to the 5 and what, what's the standard atmosphere of the current. You don't have to call it the Bureau standards to figure out to do in this class. We keep everything round to like 1 sig fig. So 15 is good enough for this, 10 to the 5 is good enough for this. And this is what I say, newtons per square meter, right? That's newtons per force, square meter for area. This is also called Pascal. This is a unit of Pascal. So I'd also write this 10 to the 5 PA. So if you see PA, that's Pascal. All right. So all those things are the same. Let's get a feeling for how big that is, though. Let's see. Oh, yeah, one more unit. Another unit is 760 millimeters of mercury. So mm cap h little g, and cap h little g, I just mean mercury like off the periodic table. It's the chemical name for mercury. And millimeters is what you expect, it's the distance millimeters. And we'll talk about that in a few minutes too, what that means. That's the column of mercury that would rise up if at the bottom you're exerting a pressure of exactly 1 atmosphere, assuming there's no pressure on the top of the column. So one thing that we have to distinguish when we talk about pressure is whether we're talking about absolute or gauge pressure. So when you all answered 1 atmosphere, there's 1 atmosphere of pressure in this room, right? That's right, but is that gauge pressure or absolute pressure? That's right, it is absolute pressure. In other words, gauge pressure is what you get. So if you have a pressure gauge for the tire on your car, right, or your bike or whatever, and you go and you measure it, that gives you an answer that's in gauge pressure. If you have a hole in your tire and it's not inflated, like it doesn't, you push on the tire, it doesn't push back, it's just got no pressure inside, no pressure inside. If you use your gauge, what will it say? Will it say 1 atmosphere when you hook it up to the? No, not on my gauge. It's 0. If I pump up my tire and I check it, it'll say whatever 30 psi. What is that 30 psi? That's like, oh, this is also called psi. Pounds per square inch. There's a million ways to write pressure. Turns out pressure is very useful for lots of mechanical stuff in different countries, so it comes up with their own unit. But anyway, so like 2 atmospheres, but those 2 atmospheres are above and beyond the atmosphere, the atmospheric pressure. Now, how do I say it? I say that gauge pressure is let's do it this way. Gauge pressure is equal to regular old absolute pressure minus 1 atmosphere. That's what I mean by it. And the reason we define that and have it as a useful concept is that most gauges work by measuring differences in pressure. So if you want to know what the air pressure is in the tire on your car, you hook up a gauge to it. What it tells you is what the difference is between the inside and outside of the car. And the outside is, you guessed it, about equal to 1 atmosphere. So it's just telling you how much pressure there is in your tire above and beyond the pressure outside the tire. So even if your tire has a hole in it, right, the inner tube is burst and it doesn't have the integrity to hold the air in, it still has an atmosphere of pressure inside, right? After all, the air inside the tire, if it had less than an atmosphere, then air outside would rush into the tire and replace it or collapse the tire. So to demonstrate that, here I've got something that has a lot more structural integrity than a tire. Here's a actually it looks like it's already undergone a little bit of deformation, hasn't it? But anyway, this is a metal can, steel can, right? There's nothing in it. And all I'm going to do is I'm going to hook it up to a vacuum pump, right? Take the air out. And we'll see what happens. I think you know what happened, but it's kind of fun to watch, so I'll go ahead and turn it on. If I can find this way, it's the hardest part of this demo. There we go. Sure enough, right? It's a lot of strength. It's pretty powerful, right? I mean, I made a mistake. I'm not supposed to do that. Oh, and I broke the thing right off. I'm not supposed to do that. Oh well, hope I didn't suck any oil out of my pump here. Oh, I'm sure they'll charge me later. Oh, that's too bad. In any case, so we've got our can, and it's so beat up. Like if I tried to do that with I should have tried initially with my hands to crush this can, right? Although you would have been very impressed when I couldn't do it, and it wouldn't have convinced you of anything. Have people come down and try to do it themselves. If I stood on this, I could have crimped it, but I couldn't have crimped it this well. Like it's like the 2 walls of this thing are flat together, right? Why is that? Well, once the pump removed the air from the inside, the air in the room is just pushing and crushing the can, right? I mean, obviously, I say obvious, although it wasn't. I think if we showed this to somebody a couple hundred years ago, they would be mystified by it and explain to them several times. You know, there's a lot of pressure in the air in the room, right? As we said, 15 pounds every square inch on here. So as if we stacked a bunch of weights and placed them perfectly to just keep pushing until it's just flattened out. And the result is that if you take the air out of the inside, right, it gets crushed. So why aren't we all being crumpled up and crushed right now? Why aren't we under terrific pressure? Well, we are under pressure, but of course the inside of us has a lot of pressure too, right? So everything inside of us is at the same pressure as the air around us, and we don't notice that. In other words, the net force on this little piece of skin right here is 0. The same amount of inward force is the same as the outward force, right? But I'm always surprised. I mean, I shouldn't say surprised. I've seen this a million times, but although you think I know how to do it by now. But it's good to be reminded how much power there is available, how big the forces are. That's why when you go into a laboratory on campus, you have big canisters of air. That are inside those canisters is several atmospheres of pressure of some gas, nitrogen or whatever it is. And even if it's not something that can burn, like nitrogen, right? It's not going to burn. It's still extremely dangerous, right? Because if that thing were to fall over and the top got knocked off, it'd be like a rocket, right? I showed you a rocket a couple lectures ago with a little plastic and water, and it shot to the ceiling, nobody got hurt, right? But if one of those things goes off, if the top comes off one of those canisters, it has a lot of destructive force, and it can take a building down. And people get hurt, and people die when those things get knocked off. That's why there's always rules about how you have to chain to the wall and everything else. Well, actually, so on next lecture we'll make a cannon and we'll describe this with ping pong balls. So we'll do that on Thursday. Okay, so there's a lot of pressure, and if it's not balanced by pressure on the opposite side of some surface, then the net force winds up being non-zero, and it can move it'll crush a can or it'll accelerate a ball or whatever it's doing. Let's see. Oh yeah. So why is there pressure in the room? What causes the pressure in the room? I mean, there's a lot of air in here, but what's holding the air there? So there's a couple ways to answer that. Gravity holds the air here, otherwise it would all escape in outer space. But the reason there's pressure in the room really is that there's a whole bunch of air above that air in the room that's pushing down on it due to gravity, right? There's a column of air above us. How high does that column go, roughly? Well, you can fly an airplane up a few miles, right? So it goes up for a few miles. I mean, being really coarse with this, but order of magnitude is about right. So a few miles of air above us. Now, how deep do we have to go in a swimming pool to achieve the same change in pressure that you experience if you go from the top of the atmosphere down to the surface of the Earth? of 1 atmosphere. So about how deep in a swimming pool do you think you have to go to get about an atmosphere of pressure due to your depth in the pool? Yeah, 10 meters. Yeah, that's about right. It's not anywhere near as much as the atmosphere. Why? What's different about air and water that makes that difference? That's right. Yeah, what's different between air and water? What does water have much more of than air? Density. That's right. And I should be careful. When I talk about air, I mean air at the temperature and pressure of this room, right? Standard temperature and pressure, whatever it's called. In those conditions, air has way lower density. Now you can compress oxygen and nitrogen down so they become liquid and then they have some more density. But at this pressure and temperature, yeah, the air in the room has the same, a much lower density. So let's be more quantitative about this. I want to talk about it because it's good to think through how these things work, right? Rather than before we get too bogged down with the equations. But the equations are going to confirm all the things we just said, right? So if we want to calculate how pressure changes as a function of height, how can we do it? Well, we can do it using the same old laws we've been using so far. Newton's second law and is going to probably be enough to get us there. Actually, one more thing I wanted to mention before one more thing I want to show before I do that, and that's just this demo over here. I don't think this will be a shocker to most of you, but it's worth being explicit about it. And that is, all that really matters is the height when you're trying to figure out what's going on with pressure. And there's a couple ways to think about that. I don't know if you can see this. The music is colored dye in here, but it's a pretty dilute dye. It's homeopathic levels of dye. You can't really see it. But can you see that the surface of the water in this right is about here, and it's exactly the same height in all three of these parts of the vessel. And that's not so surprising, perhaps, but it's worth thinking it through. A lot of students, when they go to calculate this stuff, they forget common sense. Keep your common sense intact when you're going through the calculations to make sure the answers make sense. But the height's the same everywhere. Why is, in fact, the simplest way that a physicist would express why it must be true is that no matter what crazy shape's going on, no matter how big it gets or how skinny, no matter whether it's big all the way or skinny or whether it's going at different angles, like look at the path length is much greater here, right, than it is here. But all that matters is the height. If that weren't true, suppose this were higher in here than it is here. Physicists would say, well, that can't be, because then what I could do is I could put a little bridge here and have a little paddle wheel and make a perpetual motion machine, right? And I could get energy and attack people and sell it and whatever, right? And, you can't get no free lunch, right? So the way a physicist thinks about this is, oh yeah, no perpetual motion machines, therefore it must be the height of the water must be the same everywhere. That's sort of the short circuit way to see that it can't be. Another way to do it is just to say, oh yeah, I know that because gravity is pushing straight down, and that's the same everywhere throughout this whole region here. It must be the case that that when you change your location, the only thing that's going to matter, if everything's holding still, there's no motion in this problem, everything's holding still, it's in hydrostatic equilibrium, and this is one continuous flow, if you like, one way to phrase it, one continuous flow of water. It's all connected, right? It's not just connected, but, well, all right, we'll get it flow at the end of I'm getting ahead of myself. The point is this, that if it's in hydrostatic equilibrium, all this is connected, then it's not going to, it's not possible that you could go up higher over here than over here because they're at the same height. And the only thing that's affecting the energy inside the little volumes of this water is what pressure it's experiencing and how high it is in what gravitational potential energy is, right? Those are the only two things. There's nothing else in the problem. There's no kinetic energy in the problem, and there's no other forms of energy. So that means that you know that you're not going to be able to get, for the same reason that a roller coaster, you start off at a certain height, doesn't matter what crazy track it follows, when it gets to the other side, it can't wind up at a higher spot than it started. So you can't wind up with water that's going to be higher over here. Anyway, so we'll make all this explicit now with some calculations. And we're going to start, as I said, with Newton's second law, as we often do, trying to figure these things out. So suppose we've got a tank of water, right? And it's in hydrostatic equilibrium. So we've got our tank. And by hydrostatic equilibrium, I just mean that the water is all at rest everywhere. Now, you might be bothered by that because you know from your chemistry classes, right? If you get really close, if you were to analyze individual molecules, they're moving around like crazy, right? So when I see that the water's holding still, what I mean is, so here's the water inside the tank, right? Here's the surface of the water. What I mean when I see it holding still is that on average, the same number of molecules are going to the right as going to the left through some surface. So I say how much water is going to the right or left right here. Same that way as that way. Same thing if I put a membrane now and say how much water, not a membrane, but an imaginary surface, and say how much water is going up versus down. Same thing. On average, the water's not moving, right? The average velocity of all the molecules in the water is zero. Another way to say it too is the center of mass of the water is not moving, although that's not a strong enough statement, right? Because I need to say that about every little region of the water. So I'd say every little volume of the water in every case it's not moving. So that means that I can take a little sandwich bag, like a little plastic bag, and put it around a little volume of water. Let's say I've got a bag in a cube shape. Right? Okay, here's my little volume. I'm drawing it bigger than it needs to be just so you can see it on the blackboard. But I need this to be a little infinitesimal volume. And I can say, well, what's that little volume doing? Well, if it's in hydrostatic equilibrium, it's not moving around, it's just holding still. And I can ask, what forces are being exerted on this thing? So in other words, I can make a free body diagram and apply Newton's second law. I can do the same things with fluids as I do with solids. All those rules about Newton's second law, Newton's third law, all those things are the same. And I'll ask you questions about that later in this lecture, on Thursday's lecture, and check to see whether you believe me or not. We'll see whether you believe me. Newton's laws are true for fluids. So let's think about what's going on here. If I blow this thing up, so let's draw a bigger picture of this cube so you can see it through the back of the class. I'm trying to draw up some perspective here. Right, so I've got a cube of fluid. It's got 6 sides, as all cubes do, in 3 dimensions, right? And so it's going to matter what the pressure is in different parts of the problem. So let's call this P left for the pressure over here. Let's call this P right for the pressure over here. We'll call this P bottom. This is P top. There's also going to be a pressure in the front and a pressure in the back, but I'm not going to write that in. When I make my free body diagram, right, of my little volume of water, my little test volume, or whatever you want to call it, of water, say, all right, I'll make my little dot. Let's just do it with the plain old vanilla version of a free body diagram. Make a dot, and then we'll draw our different vectors. Well, so this thing, let's give it some dimensions. Let's say that the sides are all of length L. So here's length L. That's length L. This is length L. Okay, so it's a cube of side length L. Let's make L really small, okay? Just to avoid any, well, we want to make it really small. And we say, all right, what's the free body diagram look like? Well, there's actually 6 forces due to pressures on different sides of this thing. So remember before we said pressure is just force over area. So that means we can get the force that'll go on here as being pressure times area, right? But we have to be sure that we're talking about like what direction the force is going. Just be careful about what direction the force is going, is what I'm trying to say. So pressure left over here. It's pushing on this wall over here. And if I want to know what force results, I'll say, well, first of all, which way is the force pointing? So which way is the force pointing on the block, on the little, I shouldn't say block, on the volume of water due to this over here? Right, left, up, down, in, out of the board? To the right, that's correct. So ropes only pull, and fluids can only push, right? And you might complain, well, wait a minute, over here, I suck fluid out, I suck air, it's the fluid, right?